In this video, we're going to focus on where the derivative does not exist and see when and why that might happen. So you might remember, or you might have noticed, when we defined the derivative that all of the definitions included this phrase, provided the limit exists. Okay, and as we know from chapter 1, there's lots of times when the limit does not exist. This is also true for the derivative and the limit definition. So we're going to look at a few examples. So first of all, let's think about the function f of x is 1 over x. So what if we wanted to talk about the derivative at 0? Okay, so remember that f prime of 0 is going to be if you think of the tangent line interpretation, it's the slope of the tangent line, okay, at x equals 0, or the slope of the line that's tangent to the graph f of x at x equals 0. But there's a problem here. Okay, x equals 0 is not in the domain. Okay, so this point, the tangent line, the line passes through the point 0, f of 0. Okay, but f of 0 does not exist here. So what's going on? Okay, if we think about the graph, okay, of 1 over x, it's going to look something like this. Okay, so we know that there is a vertical asymptote, okay, when x is equal to 0. So how can we have a tangent line that goes through a point that doesn't exist? Okay, this is not something that happens. So if there's no point, okay, so the point is, the x value is not in the domain, that means that there's no tangent line, which means there's no derivative. Okay, so whenever the derivative does not exist at x values that are not in the domain. Okay, so here we would say f prime of 0 does not exist. Okay, so 0 is not in the domain. So that's one way where we don't have a derivative. Okay, now let's consider the function f of x is absolute value of x. Okay, so again, we're going to think about f prime of 0. Okay, here 0 is in the domain, so that's a good start. So let's try and compute the derivative. Okay, so f prime of 0, remember, is the limit as h goes to 0 of f of 0 plus h minus f of 0 all over h. So for this function, for this function, 0 plus h is absolute value of 0 plus h, okay, minus absolute value 0 all over h. So what we get is the absolute value of h over h. Okay, now we actually looked at this limit before for x's, so let's just briefly think about it again. So let's recall, okay, that when you have an absolute value, so here it's absolute value of h, you can think about it as a piecewise function. So if h is positive, if h is positive, is bigger than 0, bigger than or equal to 0, then the absolute value of h doesn't do anything, so it's just h. Okay, but if h is less than 0, then the absolute value makes it positive, so a way we can write that is minus h. Okay, so here h is negative, so minus h is going to be actually a positive number. Okay, so that's another way to write it as a positive number. So that means that the absolute value of h over h can also be a piecewise function, but here now I can't have h equals 0, so h bigger than 0. So if I'm bigger than 0, it's going to be h over h, which is a 1. And if I'm less than 0, it's going to be negative h over h, which is a minus 1. Okay, so we get these two different limits going on. Now we can think about the one-sided limits. Okay, so as h approaches 0 from the right, okay, that means that we're bigger, h is bigger than 0. Okay, so we're in the case where it's h over h, or 1. So what that means is that this is actually the limit, so we can simplify the function to just be the number 1. The limit of a constant is just a constant. So this limit is equal to 1. And if we approach from the left, okay, the absolute value of h over h. So now when we're going from the left, we know that we're slightly less than 0, which means that we're in this interval. So now absolute value of h over h is actually minus 1. So this is the limit as h goes to 0 from the left of minus 1. And again, we're taking a limit of a constant, so we just get a constant. Now these two limits are different. So what happens when the two one-sided limits are not equal is that the two-sided limit does not exist. Okay, so the limit as h goes to 0, absolute value h over h, does not exist. Okay, but this limit was actually equal to f prime of 0. So that means f prime of 0 does not exist either. So here's another case where it doesn't exist. Now what actually happened here? So I'm going to draw the graph of absolute value x. Okay, it's like a V. Okay, so it looks like this. Okay, so this is y equals absolute value x, or f of x is absolute value x. Now, if you think about the tangent lines, so if we're bigger than 0, remember the tangent lines for a linear function are just a linear function. Okay, so they follow this line, okay, like this. So the tangent, no matter where we are on this line, it's the same tangent line. So these tangent lines all have slope equal to 1. Okay, now if we follow, we're getting close to 0 on the left, okay, the tangent line is going to follow this line. And it's going to have slope equal to negative 1. So as we approach x equals 0 in the middle, the tangent line slope is always 1 on one side and always negative 1 on the other side. So these slopes are not approaching the same number. So that means that they won't exist. The derivative won't exist, I mean. So let me just write that. So as we approach x equals 0 from either side, the secant lines approach different lines. Okay, with different slopes. Okay, so that's going to be another case where the limit doesn't exist. Okay, now what happened here in our graph, the way we could classify these when this is going to happen, is that we had a sharp turn, or we call it a corner. Okay, or a sharp turn in the graph. Okay, so notice that at this point, we were going this way, and then we just quickly changed direction, and we sort of followed a different curve. So that is the idea of a corner or a sharp turn, and whenever those happen, the derivative isn't going to exist there. Okay, let's see another example. So here our functions g of x is the cube root of x. Okay, and again, we want g prime of 0. So, can we plug in 0? Okay, so g of 0 is going to be cube root of 0. Yeah, this is fine. That's 0. Okay, so it's in the domain, so that's good. So let's try and compute g prime of 0. So it's going to be the limit as h goes to 0, g of 0 plus h minus g of 0 all over h. which is the limit as h goes to 0 of cube root of 0 plus h minus cube root of 0 all over h. So if I get rid of those zeros, I just have cube root of h over h. Okay, which I could actually rewrite. So this is the same base if I write it as an exponent. This is h to the 1/3 over h to the 1. So you might want to think about it as h to the negative 2/3. Or 1 over h to the 2/3 maybe is better. Okay, so 1 over h to the positive 2/3. Okay, so that's our limit. So now what we want to think is, what happens as we get close to 0? Okay, so again, we look at the left and right limits. Okay, so let's do the right one first. So 1 over h to the 2/3. So I'm going to do this underneath, maybe in blue here. Okay, so what happens as h goes to 0 from the right? What happens to h to the 2/3? Okay, well, h to the 2/3 is the cube root of h all squared. So maybe I don't want the arrow, maybe I want, these are equal. Okay, those are the same thing. And now I want to think about what happens as h goes to 0. So if h is close to 0 but positive, the cube root is also close to 0 and positive, and then I square it. I'm going to get a positive number that's close to 0. So I'm going to write this as 0 with a plus sign. Okay, this just reminds me that I'm close to 0 but positive. Okay, so then what I want to think is, okay, so 1 over h to the 2/3 is going to 1 over a really small positive number. So when I have a constant, 1, and I divide by a really small positive number, I'm going to infinity. In this case, it's going to be positive infinity because both of these are positive. So this right-hand limit, doesn't exist, but it approaches positive infinity. Okay, so it doesn't exist. Now we can do the same thing with the left-hand limit. Okay, so again, I'll do this in blue. So as h goes to 0 from the left, h to the 2/3, which is the cube root of h all squared, is still approaching 0, but now I'm plugging in a number that's negative. Okay, so this middle bit, cube root of a negative small number, this is going to be a negative small number, so from 0 minus. But then I'm going to square it, so that's going to make it positive, so I still get 0 from the positive side. Okay, so I'm still approaching 0, but on the positive side. So that means, again, 1 over h to the 2/3 is going to approach 1 over 0 plus, which is going to go to positive infinity. So this limit also doesn't exist, but goes to positive infinity. So because those are the same, our two-sided limit we would write is going to positive infinity as well. Okay, so they don't exist. But infinities don't exist. Okay, so this means that the g prime of 0 also doesn't exist. Okay, so because our limit doesn't exist, the derivative at that point cannot exist either. Now, what does this look like in the graph? So if I were to sketch this graph, it goes through 0. I'm going to call this 1 and this negative 1. So it's 4 spots away. This is positive 1. Okay, so I go through these points here. Okay, so what happens in this graph? You go through this point and then you get oh, I didn't do a very good job. so this point is just really steep. And then it levels off. Okay, so this is what the graph looks like for cube root of x. So if we think about our tangent line at this point, okay, it's actually vertical because it's so steep. Okay, so this is another time where the derivatives don't exist. So derivatives also do not exist at x values where the graph has a vertical tangent line. So, as a summary, okay, the derivative f prime of x exists at each of x value where f is continuous, okay, so that means f of our point A exists, okay, and the limit as we go to A of f of x is also f of A, so that's what it means to be continuous. Okay, so it's in the domain and it's continuous. And then we say is smooth. Okay, so what we mean by smooth is there's no sharp turn, okay, or corner. So it's nice and fluid to draw, and it does not have a vertical tangent line. So said another way, which maybe is easier to think about, the derivative does not exist for x values where it's discontinuous. Okay, or it has a sharp turn. So these are now ors instead of ands. Has a sharp turn / corner, or it has a vertical tangent line. Okay, so having any one of these is enough to say that the derivative does not exist, and we would say it's not differentiable at that point. So let's just quickly look at this example. So we want to think about for what x values would the derivative not exist. Okay, so I've labeled a couple of points here. So first, I'm just going to go from left to right. Okay, so first of all, so not differentiable. Differentiable at. So the first one is -7. Okay, when x is -7, okay, this is a sharp turn. Okay, so that's a bad thing. So there's no derivative there. Okay, also -5. Okay, so at -5 there's a jump, which means not continuous. Okay, so that's enough to be not differentiable. -1, okay, there's a vertical asymptote. Okay, so it's not continuous. Okay, what about at x equals 2? This is one that sometimes confuses people. What does the tangent line look like at that point? Okay, it's almost level. Okay, so the tangent line is actually horizontal because we leveled out there. Is the slope of a horizontal line bad? No, it's 0. The slope is 0. Okay, so that actually means not only does f prime of 2 exist, okay, but it actually equals 0. Okay, so we actually know that one. Okay. What about at 4? So x equals 4. It actually doesn't exist there. Okay, so at 4, maybe I should do this in a different color. At 4, I tried to draw this vertical. Okay, but we're getting a vertical tangent line here. Okay, so that's why that doesn't exist. Okay, now what about x equals 7? So the graph is almost smooth, except there's a hole that's been moved, okay? This is not continuous. Okay, it's a removable discontinuity, so it's kind of like almost the best type of discontinuity. Okay, but it's still discontinuous. So not continuous means not differentiable. Okay, so you want to remember that. Maybe I should write that here. Let's do it in black so it stands out. So differentiable implies continuous. Okay, you have to be continuous in order to be differentiable. So not continuous implies not differentiable. Okay, but it doesn't mean that if you are continuous that you have to be differentiable, as we saw at x equals -7 and x equals 4. Okay, and if you're not differentiable, that doesn't mean you're not continuous. Oh, that's what I just said.